In the last video, we discussed why the Ross Ice Shelf is important to study in terms of sea level rise. However, the Ross Ice Shelf is one of the largest ice shelves in Antarctica, so we need to make decisions about the best place to study to measure changes. My fieldwork takes place on the McMurdo Shear Zone, an area of ice between the Ross Ice Shelf and the smaller neighboring McMurdo Ice Shelf. As the fast ice on the Ross Ice Shelf side flows past the slower moving ice on the McMurdo side, it begins to break apart from pulling and stretching, forming what's known as a shear zone. The shear zone is an important place to study ice shelf stability because it's the western boundary of the Ross Ice Shelf. The shear zone supplies an important amount of friction to the side of the ice shelf, limiting its motion. If the friction in this area is changing with time, it could affect the flow of the ice shelf and the amount of resistance it provides to the glaciers that feed into it. Our field site within the shear zone is only 50 kilometers from the United States Antarctic Program's largest base, so it's relatively easy to get to study. So what data do we need? We'll use our research questions to guide us in our investigation. Is the Ross Ice Shelf speeding up or changing its flow pattern? One way to study this would be to track a point on the surface of the ice, measuring its changing position over time. This will help us determine the ice velocity within our field site. As you might imagine, this ice is moving quite slowly. In order to get accurate velocity measurements, we drill an array of poles into the ice and track how they move on a yearly basis using GPS receivers like the ones found in cell phones, cars, and tablets. We would also like to study processes that are happening inside the shear zone, such as crevassing. Are there indications of cracking and crevassing within the ice column that could tell us about the stability of the ice shelf? If we can observe changes in crevasse size, distribution, and orientation, we can infer changes in the friction that's supplied from the shear zone to the Ross Ice Shelf. The technique of ground penetrating radar, or GPR, is commonly used to study ice at depth. GPR works similar to sonar. A transmitted device sends a radio wave into the ice. This wave propagates or travels into the ice until it comes in contact with a crevasse. The wave then bounces off this crevasse and is received by a receiver device. The time between when the wave leaves the transmitter and is picked up by the receiver can be used to determine where the crevasse is or at what depth, as well as information about its size and orientation. In order to conduct a GPR survey, the device is typically dragged across the surface of the area of interest. While the McMurdo Shear Zone is a relatively easy place to get to, it's a dangerous place to study despite appearances. If you look across the surface on the ice shelf, it appears very flat. This is because of snow bridging, or an area of snow that covers a crevasse. Often these snow bridges are thick and the risk of breaking through is minimal. Other times they are very thin and are incredibly dangerous. One hazard of our field site is that it's completely flat, and we have no way of knowing if we're on stable ground or on top of an unstable ice bridge. As you can imagine, this makes studying our field site very dangerous. Just to illustrate just how dangerous this can be, I'll share a story from the Antarctic program's past. One of the first observations that the shear zone was becoming unstable was accomplished by a tractor named Linda. In 1990, Linda was attempting to cross an area of the shear zone that was believed to be safe. On board were Quentin Roten and Brian Weeder, contractors from both the United States and New Zealand Antarctic programs. Linda was towing a sled with approximately 25,000 pounds of dynamite. Well, you can see where the story is going. The tractor plummeted 15 meters into a crevasse, and Brian and Quentin watched for more than 3 hours as a sled with explosives hung precariously above them, teetering on the edge. A joint effort by both programs was able to safely retrieve both people on board as well as the dynamite. Linda, however, would remain within the icy depths of the shear zone. This story aside, it's easy to see how safety can be an issue within the shear zone. Let's return to the topic of GPR. How exactly will we get this detailed data set if skiing across the surface could lead to plummeting into a crevasse? Meet Yeti, a lightweight, four-wheel drive, battery-powered robot specifically designed by the Dartmouth Thayer School of Engineering to tow GPR. Similarly, we need to take precautions during our GPS survey. Much of the survey will be on a safe portion of the shear zone. We will travel there on snowmobile and we will have harnesses on at all times, as well as crevasse safety gear. For the more dangerous part of the shear zone, we will use helicopter assistance. We will be roped up to the helicopter at all times, so we will already be attached to a rope in the event that we break through a snow bridge. So now that we have an idea of the problem that we hope to address in the shear zone, as well as the data that we need to obtain, in the next video, we'll talk about the planning process for our trip. I'll leave you with a few questions to think about for next time. What other applications could we use GPR and Yeti for? And what places do you think it would be helpful to send a robot instead of a human? Thanks for following along. I can't wait to hear your questions for this week.